Welcome to a related rates example. So in this example, a snowball is melting. The volume of the snowball gets smaller by 1 cubic centimeter per hour. And our job is to figure out when the snowball is 6 centimeters in radius, how fast is the radius of the snowball changing? So the first thing I like to do anytime I'm doing an application problem is just kind of understand the situation. So understand the problem. So we're dealing with a snowball. Presumably snowballs are spheres. Right? And then if we look at the radius versus the overall volume, the radius is shrinking and the volume is shrinking. So the radius is shrinking. Right? It's getting smaller and the volume is shrinking. So the volume is shrinking. By 1 cubic centimeter per hour. We want to know the rate of change of the radius when the radius equals 6. Okay. So at this point, we have sort of a summary of the information from the problem. You can use shorthand notation. You can switch to symbols at this point. That's up to you. Once we have all this information, we're going to sort of identify the known symbols and also find the relevant formula. So if we identify the known symbols, I'm going to say the known and unknown, or the known symbols and what we want to know. Let's go with that. So the volume shrinking by 1 cubic centimeter per hour. What this is telling us is the change in volume, or the rate of change in volume, dV/dt. We have a 1 for 1 cubic centimeter per hour. And then because it's shrinking, volume is getting smaller, it's decreasing. We should have a -1. Right? Volume is decreasing, so derivative should be negative. And then we want to know the rate of change of volume, of radius. So the rate of change of radius, we're looking at dr dt, if r is the radius, when the radius is 6, so when r equals 6. So next up, what we're going to do is we need a formula that relates these variables. So find a formula that relates the variables. So in this case, the variables that we have are V, which is the volume of the sphere, and R, which is the radius. So volume of a sphere is simply V equals 4/3 pi r cubed. The last video of this section will be sort of a series of formulas that may be useful. So I'll have some volume formulas, some surface area formulas, and go from there. But for this case, the formula we're looking at is V equals 4/3 pi r cubed. Once we have that formula, then our job is to find the equation that relates the rates. So we're going to differentiate with respect to time. So we have, if we differentiate with respect to time, we have ddt of V is equal to ddt of 4/3 pi r cubed, or dv dt is equal to 4/3 pi times, we would have 3r squared and then times dr dt. And if we simplify, we get dv dt is equal to 4 pi r squared dr dt. At this point, we have our formula to relate rates, and we can go ahead and plug in all the information we were given to find what we want to find. So we're going to plug in the known information and solve for what we want. So we have the following relevant information. We have dv dt is equal to 4 pi r squared dr dt. We know that dv dt is equal to -1, and we want dr dt when r equals 6. So the things that we can go ahead and plug in, we have dv dt is equal to -1, so we can swap out dv dt. And we have r equals 6, so we can go ahead and swap out r for 6, and then all that's left is that dr dt. So we have -1 is equal to 4 pi times 6 squared times dr dt. Or -1 is equal to 4 times 36. We would be looking at, let's see, 24. Then 4 times 3 is 12 plus 2, 144 pi times dr dt. And so we get that -1 over 144 pi is equal to dr dt. And then at this point, I'm just going to do a last step, which is our sort of conclusion back in context. So I think I'm on step 6, yeah. So put it back in context. make sure the problem makes sense. Or the answer makes sense. So if the radius is decreasing, or sorry, if the volume is changing in cubic centimeters per minute, all of our measurements were in centimeters, then presumably the radius, or what units did we do? Minute or hour? Per hour, sorry. So the volume is changing in cubic centimeters per hour. So the radius should be changing in centimeters per hour. Since every other measurement we used was in centimeters. So what we get is the radius is shrinking at a rate of 1/144 pi centimeters per minute, sorry, per hour. Or if we plug that into a calculator, we wind up getting 0.002 centimeters per hour. When the snowball is 6 centimeters in radius. So this is a very slow change. If you think about it, if a snowball is 6 centimeters in radius, it's a fairly good sized snowball. And 1 cubic centimeter is going to be just a very little portion of that whole volume. And so the volume itself, even if it's changing by 1 cubic centimeter, the snowball is barely changing at all. So presumably it's still extremely cold out and the snowball is melting very, very slowly. It makes sense that we got a negative since the volume was shrinking, the radius would presumably shrink